Now we're ready to start with advanced kinematics. What makes these problems advanced is that generally you have two or more objects that somehow are doing something simultaneously, and then there's something that happens that brings them together at a certain instant in time. And there are all sorts of questions that might be asked about what's going on at that instant in time. There are three numerical examples we're going to be taking a look at, and we'll look at them one at a time. As is so often the case in a lot of these problems, one of the key features that we're going to need to be able to handle is the amount of time that's involved with the evolution of the system. So go for the time in these problems. Let's take a look at our first example. A helicopter is traveling vertically upward with a constant velocity of 5 meters per second. A package is dropped straight down from the bay of the helicopter at the instant that the helicopter is 20 meters above the ground. The helicopter continues to travel upward with a constant velocity of 5 meters per second. Determine the separation between the helicopter and the package when the package hits the ground. Oh my word, how in the world are we going to solve this problem? Well, let's begin with a good diagram. So I've got a helicopter. A person standing in this helicopter will do something when the helicopter is 20 meters above the ground. The helicopter is moving upwards at a constant velocity of 5 meters per second. Now someone is riding along with the helicopter and is going to drop a package outside the bay of the helicopter. I'm symbolizing this package with an orange box. So now what happens? Well, the box and the helicopter both share the same initial motion. Both of them are initially moving upward. The package is released, though. It's not going to move upward with a constant velocity. It's going to rise a bit as if it were tossed upward with an initial speed of 5 meters per second, and then it's going to fall until it gets to the ground. In the meantime, the helicopter is going to be continuing to move upward at its constant speed. What we want to know in this problem is how far apart the package and the helicopter are when the package hits the ground. In our picture, we're trying to figure out what the distance is between the bottom of the helicopter and the ground when the package hits the ground. A lot of times in these problems, the hardest part of the problem is figuring out what in the world it is that they're asking you. Now we have two objects, and both of these objects are going to be in motion at the same time. Their motion is going to be different from each other, so I'm going to look at information about the package separately from the information about the helicopter. Let's start with the helicopter. The speed of the helicopter as it moves upward is 5 meters per second. I'm going to call that V with a subscript H for helicopter. And at the instant that the helicopter releases the package, it's 20 meters above the ground. At some point, you're going to have to make a decision about where you set the origin of your coordinate system. And there are several different possibilities. If you want to make the origin of your coordinate system where the action begins, then the helicopter moves in the positive direction, and the package ultimately is going to end up on the negative side of the origin. Alternatively, you could make the ground level the zero position and make the initial position of the helicopter plus 20 meters and let it continue to move upward. But you've got to make a decision about where you're going to set the origin of your coordinate system. To be consistent with the way I've solved these problems before, I'm going to let the action begin at x equals 0, or in this case y equals 0, since we have vertical motion. And I'm going to set the origin of my coordinate system the place where the package has been released. I'm going to call up the positive direction and down the negative direction. Let's focus on the package now. The package, after it's released from the helicopter, experiences free fall acceleration, and it's accelerating in the downward direction, which happens to be negative. And since it's under free fall motion, then its acceleration is negative 10 meters per second squared. Since the package is moving upward with the helicopter before it's released, then it shares the helicopter's initial motion. And so the initial velocity of the package is also going to be plus 5 meters per second. And since it starts at the same position that the helicopter does, then its initial position is also going to be at the origin, y equals 0. Now what? Well, if we could figure out how much time, remember, you're wanting to go for the time in these problems, if we could figure out how much time it takes for the package to get from where it's starting to its final position, which is 20 meters on the negative side. We need to add that to our package information. That amount of time is going to be the same amount of time that the helicopter is going to be moving upwards at plus 5 meters per second. So we could figure out the position of the helicopter in that amount of time. And then we could take those distances, the 20 meters that the package has fallen, plus whatever distance that the helicopter has ridden, and add those two numbers together, and that's going to be the distance between the helicopter and the package when the package hits the ground. So we want to figure out how much time does it take for the package to fall 20 meters. Since this is an object that is experiencing constant acceleration, we can pull out one of our equations of motion to help us out. And I'm going to suggest the second equation of motion, y is equal to y naught plus v naught times t plus 1/2 a t squared. We know everything for the package in that equation except the time. So this turns out to be a quadratic equation, and you could use the quadratic formula to help you figure it out, or you could plug the numbers into your TI solve. Let's put the numbers in. I'm going to use TI solve. Now pull out your TI 89 and put it into TI solve. There are two roots. One of them is meaningful, the other one is not meaningful. In our context, we want the positive root. In other words, the amount of time it takes for the package to fall 20 meters from where it's dropped from this moving helicopter is 2.5 seconds, roughly. Okay? Now what? Well, the helicopter is moving away from its origin at 5 meters per second, and it moves upward for 2.56 seconds before the package hits the ground. So how far will the helicopter have risen in 2.56 seconds? You can say that the position of the helicopter is equal to the initial position of the helicopter times v naught times t plus 1/2 a t squared. Well, the helicopter is moving up with constant velocity, so there is no acceleration of the helicopter as it's moving upward. Distance is equal to rate times time is what that equation eventually comes to. So there's my equation of motion. But since the helicopter is moving with constant velocity, acceleration is 0. The initial position of the helicopter is at the origin, so I get this equation. And now I know the numbers on the right-hand side, 5 meters per second and 2.56 seconds. When I put those numbers into my calculator, I get that the helicopter has risen 12.81 meters. So if I go back to my diagram, what I find is that this distance between where the helicopter began when it released the package and where the helicopter is when the package hits the ground is 12.81 meters. Well, now what was the original question? The original question is how far apart are the helicopter? I can see that I'm going to add the 20 meters to the 12.81 meters, and I'm going to get 32.81 meters. That's the total distance between the helicopter and the package when the package hits the ground. That's the solution to this first problem. Let's go on to the next example. A police officer at rest in her car observes a car exceeding the speed limit. The speeder has a velocity of 20 meters per second and is traveling in a straight line. The police officer begins to accelerate from rest at 3 meters per second squared at the instant the violator is 15 meters ahead of her. Assuming both cars maintain their motion, how far from the police officer's initial position will the cars overlap? As is so often the case in problems like these, a good diagram is going to go a long way. What I want to do is I want to sketch a bird's eye view of this situation in which I show the police car, which I'm going to represent in blue, since the police cars have blue flashing lights, and the other car are being looked at side by side. Since the question asks us how far from the police car's initial position will the cars overlap, in other words, where will they be side by side, I'm going to set the origin of my coordinate system to be where the front of the police car begins its motion. That's going to be x is equal to 0. I'm going to make the other car red in color, like a red, fast red sports car. And they tell me that this car is 15 meters ahead of the police car when the police car starts to move. The initial speed of the other car is 20 meters per second. That speed is going to remain constant throughout, because both cars are going to maintain their motion. I'm going to indicate the violator's motion with a subscript V. The police car motion I'm going to indicate with a subscript P. The initial position of the violator is 15 meters in front of the police car, so I'm going to say that that position is 15. The police car is starting from rest, and the police car has a constant acceleration of 3 meters per second squared. Now, at some time later, the two cars are going to be side by side with each other. When it's said that the two cars overlap, what we mean is that they reach the same position. Now, what are we trying to find? We're trying to find how far from the police car's initial position with the two cars overlap. In other words, we're trying to find this distance. You can call that distance X police car if you would like to, because the position of the police car when it is overlapping with the other car is going to be how far that the police car is moved since it began its motion. Okay, so now what? Well, why don't we see if we can figure out what the equation of motion for the police car is and what the equation of motion for the other car is, and see if there's something in common that they have with each other. So I'm going to write what is the position of the police car in terms of its equation of motion. The second equation of motion gives me this x is equal to x naught plus v naught t plus 1/2 at squared. There's some things that disappear from that equation, and so I can simplify the police car's equation to x is equal to 1/2 at squared. What about the sports car? I can use the second equation of motion to talk about the sports car as well. But because the velocity of the sports car is constant, the acceleration term drops out. And my violator's equation of motion simplifies to x is equal to x naught plus v naught times t. Now what? Well, what I claim is that at the time in question, that those two positions are going to be equal. In other words, they are going to overlap. So I can set the position of the police car and the position of the violator's car equal to each other and figure out at what time does that happen. And then, once I've got the time, I can substitute that time into either equation of motion and figure out the position. On the other hand, if you would like to, you could solve one of the equations for the time, substitute it into the other equation, and then solve that equation for the position. Doesn't matter which. I'm going to go the first way. Set the positions equal to each other, figure out the time, and then substitute that time into one of the equations of motion. So I'm saying let the police car's position and the violator's position be equal to each other. There's my substitution. Now I'm going to use TI solve because this again is a quadratic formula. And TI solve will help me with this. Let me put in the numbers. I get two roots. One of those roots is not meaningful. And so I'm going to keep the other root and then substitute that into one of the other equations. I'm going to take this time and put it into the police car's equation. And now I'll substitute the numbers into the calculator. I get that the police car has gone 296 meters approximately to catch up with this violator